hope that in the future my postdocs can also join you. And then as a beginning of the discussions, I'd like to share with you what we are doing in the University of Tokyo now. And as you can see in the title, I'm very much interested in their, not only the typical, their consciousness, but also atypical consciousness. To be honest, I don't use the term of consciousness in my research usually, because the consciousness, the term is not so easy to define from the computational point of view. But what I'm doing in the University of Tokyo is very closely related to what Kanai-san is doing in his CREST project. I also have my CREST project since 2016, and then we got to know each other very well within these CREST collaborations. So today I'd like to share our computational neuroscience studies from their perspective of the how their consciousness or their perceptual, the consciousness can be achieved by the neural network model, and how we can also understand the underlying neural mechanism of their consciousness or atypicalities in a consciousness from the computational perspectives. By the way, I haven't used the microphone, but is it okay for you, or should I use it? Okay? Okay, good. So I'd like to start with the, I'd like to start with one picture that is very familiar to you. So I just follow one picture from the internet. This is Kanai-san's. And there, of course, you can recognize this is Kanai-san. He looks very nice, very kind, very smart. So that is your conscious, the perceptions about the Kanai-san's image. But what happens if the image looks like this? I just modify the contrast of the image. Now you can see the very highly contrasted images. Now I think that it gets a bit difficult to even identify who he is or what emotional expression he is showing. It's a bit scary. Maybe he is getting angry. Just by changing the contrast, how you perceive their image gets very different from the original images. And we learned from our study is that there are some people who have visual hypersensitivities often see the world like this. They often see the world with a very highly contrasted in the image, and also they sometimes see the many dotted noises in the visual world, which creates the different or the atypical, the conscious experiences in their daily life. And what I want to focus here as this kind of the hyper-atypical, the visual sensitivity is mainly observed in the autism spectrum disorders. As you know, the autism spectrum disorders is characterized by their impairments in the social difficulties. So they sometimes show their disabilities in making the contact with others, for example, reading the intention of others, also difficulties in establishing a joint attention, which is very important experiences for young children to establish the social communications. But then there are recent studies that are suggesting that their atypicalities does not exist only in the social, like a higher level cognition, but also the lower level perceptual signals. So as you have seen in one picture before, just in hypersensitivity in the vision is one of the typical patterns in their visual experiences. And also here you can see another example. You can see their bigger picture or bigger letter consisting of the smaller letters. And the question is which letter, larger one or smaller one, becomes more conscious in your mind first. And then researchers found that typically developed persons tend to first look at the global picture, global letter, whereas the persons with autism spectrum disorders pay first attention to the local letter, which is called the local processing biases. So for example, the person with ASD first recognize H instead of S, the bigger pictures. And such a local processing biases happens not only in the recognition of letters, but also the recognition of face. So I have shown you the Kanai-san's picture. You can see that it's in face. But the persons with ASD often have difficulties in recognizing face because the configurations of faces are often destroyed in their perception. they recognize eyes, nose, mouth independently, but there is no configural relationship between these such facial features. That's why they also have difficulties in recognizing the persons or recognizing the emotional state. So the question is where this kind of the local processing bias or the atypical, the perceptual experiences come from in the ASDs. And we learned that there are some researchers, sorry, can you stop the sound? Can you stop the sound? Sorry. I'm not sure. Sorry, I can control here. Thank you. Thank you. So I learned that there are some researchers who have autism spectrum disorders started their research about themselves. It is called Tojisha Kenkyu. It's a Japanese term. As far as I know, there is no English, the corresponding term yet, because this research field is very new and it started in Japan. So we don't have the English term yet. If I directly translate this Tojisha Kenkyu into English, which is called first person study, the first persons who have the developmental disorders investigate their own consciousness experiences or perceptual experiences from the first person perspectives. That is the Tojisha Kenkyu. And this video shows how they organize the Tojisha Kenkyu. They invite not only researchers, but also ordinary people who have autism spectrum disorders. And they have their monthly meeting where their participants share their own experiences or their own difficulties or how they cope with the difficulties and so on. And then by taking their philosophical, approach, their a phenomenological approach, they studies how the participants with ASD have their problems with their social situations and how they try to cope with such problems. And the meeting is conducted there since 2011, and we had already more than 2,000 the participants to collect their phenomenological data from the persons with ASDs. And also I want to show you the one examples what kind of result or summaries they could get from the Tojisha Kenkyu or first person study. This is the one studies conducted in 2019, and to this day they discussed how they feel their body, how they feel themselves when they are alone. So there is no contact with the social environment. So from the picture you can imagine that how they discuss about themselves, their body images. For example, the one showing that there are some persons feeling that their body representation or body, their ownership is lost when they are alone. So their self-body representation or self-body image is very fragile. Depending on the social context or environmental context, their awareness drastically changes. That is one example. Or another example, this line indicating the very strong and clear wall between the self and others. Some persons with ASD describe that they have a big barrier or a big gap between their own bodily image or the self and others. That might be the one reason why they are not well contacted with the other persons. They may have their difficulties in, for example, they're applying their own internal model to interpret their other person's internal mind or intention and so on. That might be there described as a big, very strong barrier between themselves and others. So these are the phenomenological studies about their self-consciousness in their Tojisha Kenkyu. And another example showing that there are persons with ASD often have the difficulties in their feeling hunger. I think the most of you immediately recognize your hungerness. Maybe you get a little bit already hunger now as it gets close to the dinner time. But persons with ASD say that they first realizes many low-level sensory signals, like an itchy scalp or bodily immobile abilities in their bodies, or sometimes they also have like an emotional feeling like sadness and so on, or they also recognize how their stomach is moving. But then they have difficulties in making their interpretations about their sensory, the bodily sensory state. Then they have to very consciously process their bodily state in order to make the feeling of hunger. After I hear this story, I also realized that, we humans do not have any specific sensor which directly detects hunger. Actually, we all also have the similar experiences. We realize it's their body temperature, the movement of the stomach, and so on and so on. And then by integrating such a low-level sensory signal, we also realize whether we are hungry, or we are sad, or we are happy, and so on. Such a higher level social cognition also requires the process of selecting and integrating their low-level sensory signals. But what we know from their ASD studies is that the persons with ASD often have difficulties in these processes. So how they become conscious about their bodies is quite different from the typically developed person. This is another example about the body ownership. And then after studying this kind of their ASD research, I came up with the ideas to integrate our computational approach with Tojishar Kenkyu. Because the Tojishar Kenkyu provides us a lot of insight into the phenomenological and the behavioral experiences in ASD. So it helps a lot us about how we should design or we should understand the consciousness about our body or our social relationship from the phenomenological viewpoint. And on the other hand, the computational modeling helped us to test the hypothesis. The computational modeling basically design the neural network models, which inspired by the human brain mechanism, and then by modifying the model parameters in the network model, we can test how and whether such model parameters modification may influence on their behavioral aspect or their phenomenological aspect. So by integrating this complementary approach, we thought that we can better understand the underlying their neural network model or neural model or the underlying principles for their autism spectrum disorders. Of course, our intention is not understand only the autism spectrum disorders, but also the typical development as well. But then by integrating, by combining these two approaches, we can better understand, we can get a better insight into the underlying principles of ASD. That's what I started in 2016 as a class project called Cognitive Mirroring, and then we try to find out the principle of the human brain and also what causes the neural modifications causes the individual differences between the typical development and autism spectrum disorders, which also further help us to design the assistive systems for the developmental disorders. And then the next question or main question of my project is, what can be the potential principle of our human brain, which can explain the diversity between the typical development and autism? And then as a potential principle of the human brain, we are now focusing on the theory called predictive coding. I guess that some of you know the predictive coding theory, which was originally proposed by the Carl Freestone and Andy Clark. The key ideas of this predictive coding is that our human brain works as predictive machine. So of course, when we perceive the world, our human brain receives the bottom-up sensory signal from the environment. That's the bottom-up process of the perception. But we don't simply rely on this bottom-up signal. We also apply our top-down predictions to better perceive the world. That's the key ideas. Here I give you the simple illustrations of the predictive coding theory. So here our human brain has an internal model which was trained through our own sensory motor experiences, and this internal model receives their sensory signal as an input, and if you detect some prediction error, That's a discrepancy between the incoming sensory signal and your own predictions. We can update your internal model to modify and better interpret the world. That's the first process of the minimizing the prediction error, which is so-called perceptual inference. And another important point of this theory is that our motor behaviors can be also explained based on the same mechanism or same ideas. You can now focus on this motor output side. This motor output, according to this predictive coding theory, the motor output is also dominated by the process of minimization of prediction error. So for example, if you see some discrepancy between the incoming sensory signal and top-down predictions, on one hand, you can update your model, but on the other hand, you can also change the world so that the world becomes closer to your expectations. So based on these ideas, or according to the active inference, we can explain how we create our actions, how we generate our actions based on the process of the prediction error minimizations. And we think that this predictive coding theory provides us the basic principle of our human brains, and then maybe there are some modifications in the predictive processes may explain the diversity, individual diversity between the typical development and the autism spectrum disorders. That is the starting point of our computational studies. For those who are not so familiar with the predictive coding theories, I want to give you one example which nicely demonstrates how your brain also works as a predictive machine. By the way, do you know this illusion test? Could you raise your hand if you know it? Or could you raise your hand if you don't know it? Okay, great. So I ask the persons who don't know these illusions, please answer to my very simple questions. So now you can see the green cylinder on top of the checkerboards. And the question is, you can see the A and B regions. And the question is, which square looks brighter? You can compare this region A, region B, just directly comparing the grayness or the brightness of these regions. And then, which do you think more brighter? B. Else? Okay. All things B. Why? Why do you think B is brighter?
I just see it.
Okay, great. That's actually the way how your brain works and how you also rely on your predictions. The answer actually is it has equal brightness. Region A, region B has exactly equal brightness. Now I put the two gray lines here, which has the grayness here. So now you can better compare the brightness of region A and B, and they have exactly the same brightness. But without these bars, actually even for those who know this illusion, still people see B is brighter because you have the knowledge about this checkerboard. B region corresponds to the white area on the checkerboard, whereas the A region corresponds to the black area. So even with this shadow caused by this green cylinder, you expect that B must be still brighter than A. That's how your predictive brain works. If you, for example, relies only on the sensory incoming signal, so like this, if you just utilize the information about the sensory signal, you should be able to answer that A and B has equal brightness. But as your brain produces the expectation about the world, that's why you have this kind of illusions. B looks brighter than A. That's an illusion caused by your predictive brain. So everyone's brain have these predictive abilities. But the question is how this predictive ability could be different between the person with and without developmental disorders. And of course, there are many researchers, especially in the neuroscience, have been very much interested in these theories. And there have been several hypotheses have been proposed in the neuroscience. First, I want to re-explain the idea of predictive coding based on the Bayesian inference. So here you can see the 3 Gaussian distributions. Each of them corresponds to their predictions, sensory incoming signal, and the perception. So here first you can see the yellow Gaussian distributions, which corresponds to our top-down prediction, which is so-called prior here. And this variance in the Gaussian distribution explains how sure or how certain your prediction is. If you are not familiar with the environment, your predictions is not so accurate enough. So in that case, you have low precisions in your predictions, which is described as larger variances in the prior. Or also the bottom-up sensory signals, that's like a visual input or auditory input. It can also have some noises. That's why the sensory signals is also described or illustrated as a Gaussian distribution here. And this Bayesian theories based on the predictive coding explain that perception is produced by integrating the bottom-up sensory signal, this red one, and the top-down predictions. So by looking at the mean of these Gaussian distributions and also the variances, you can integrate 2 Gaussian distributions to make the perceptual, the curve. So in this case, the bottom-up sensation is more reliable, more accurate. That's why your perception is a little bit biased to the sensory signal. So this is our basic ideas of the predictive coding based on the Bayesian inference. So what happens in the autism brain? The researchers have been suggesting mainly 2 theories. One is called hypo-prior hypothesis, and the other is called reduced sensory noise hypothesis. So first hypothesis, called hypo-prior hypothesis, as the name describes, the prior get weaker with the higher variances. If you are uncertain about the environment, your prior, your predictions get very weak. So you cannot rely on your predictions. Instead, you have to rely on the incoming sensory signal. For example, that you are the beginners of the baseball player. You cannot predict where the ball is coming. So you have to wait until the ball approaches to you. And then after that, you can try to hit it. If you are the very experienced person in baseball, you can predict where the ball should come based on the trajectories. So in that case, you can rely on the priors. But this theory says that the persons with ASD seems to have difficulties in forming the priors or the internal model. That's why the persons with ASD often shows their hypersensory sensitivities because of the strong bias to the sensory incoming signal. That is one first theory. And another theory explains the same outcomes, but based on the different potential cause, which is the reduced sensory noise hypothesis. So as you have the 2 Gaussian distributions, one is prior, the other is a sensory signal, you can of course think about the modification on the sensory side. And this theory says that the sensory signal might be already different. They are more precise in ASD. That's why the perception in ASD more strongly biased to the sensory signal. That can be another potential cause for the hypersensory sensitivities. Then I thought that, okay, these are very nice starting point of our computational study, but then we think that not only the hypo-prior, but also the hyper-prior, another extreme of their perceptual differences, can happen in the ASD. So then we started testing our hypothesis. What happens if we modify some model parameters regarding the hypo-prior or hyper-priors in the neural network model and observed how such a hyper or hypo-priors would influence on the learning performance of the computational neural network model to test the hypothesis. So in the second part, I want to show you 2 studies of our neural network models. And then I want to show you how not only the hypo-prior, but also hyper-prior could explain the diversities of their autism-like behaviors. By the way, if you have any questions, please don't hesitate to ask meantime. Is everything clear to you so far? Or do you have any question? Yeah, sure.
Can we go like in a few slides back where we have this neural network architecture? I think it was somewhere, maybe 3 slides ago.
3. This one?
Yeah.
Oh.
It's, can you explain a little bit what's the input and the output of this computational model?
This is the computational model. Yeah, I would just explain this what design that we had in the second part. Yes, I will give more details about the computational model. Just this slide gives you the key basic ideas, yes, abstracted descriptions. Okay, so I want to move to the second part, which directly studies this network model. So first we introduced the network model proposed by the Professor Juntani. I think that Professor Juntani also gave talk in this consciousness club. And he's very familiar for the neural network design, which mainly inspired by our brain activities and also the predictive coding theory. And we introduced the network model called stochastic continuous time recurrent neural network model. The name is too long, but then the key idea is very simple. So as you know, the recurrent neural network model has the capabilities to predict the next time step signal. That is the basic abilities of recurrent neural network model. In addition to the prediction of the next time step signal, this network, SCTRNN, can furthermore predict the variance of the predicted signal. For example, if you train the networks to draw some like circles or H-shape in the 2D spaces with some variances, you will recognize that the variances must be also important. For example, imagine that you want you to train the networks to showing that it can be reaching behaviors in the environment. In order to grasp an object, the grasping point must have very low variance because the object is here. Your hand should be always here at the end of your arm movement. But while moving, you can take this trajectory, or you can also take these trajectories. So the beginning part, the early part of this trajectory can have larger variances. So in order to better train the network with some temporal trajectories, it's beneficial for the network to also make a prediction about the variances, the potential variances in the signal, in order to not to destroy the training. For example, if you very precisely update the network in order to minimize the prediction errors for the large variance areas, the network should destroy their internal representation because the larger variance should not be necessary to be more correctly explained by the network model. So by adding the one more modules on the output side, and then let it predict the variances of the signal, they found that Professor Juntani and Professor Ogata showed that the network can better achieve the desired goal. That's the key idea of stochastic continuous time recurrent neural network model. And then based on this network model, we thought that we can nicely test the hypothesis of the hypo-prior and the hyper-prior, because this variance allows us to control how much the network model relies on its own predictions or incoming sensory signal. When you train the network and also when you utilize the network makes a prediction first, and then this predict signal can be utilized as a prior of your model. And then this prior is combined with the incoming sensory signal, which nicely replicate the ideas of predictive coding, and also with this variance, we can test how hypo and hyper-prior in these predictions would influence on the learning. So we conducted several experiments, and one experiment their control the weight on their signals, the input signals and the predict signals. And then we observed how the parameter modification would influence and the learning performances. Here is the result. There are two lines showing that first the output behaviors of the network model, the second line showing the internal representation of the network model. So first, please look at the first line. So here we control the chi parameter. The smaller chi values corresponds to the hyper-prior, because the chi modifies the variances or how strongly the network relies on its predictions. So the smaller chi values can replicate the idea of hyper-prior here. And then if you go to the larger chi value, you can replicate the ideas of hypo-priors. So first, if we look at the first line, you recognize that the network model with normal prior or hypo-prior, they were somewhat successful in achieving the desired behavioral patterns. What we trained to the network is this circle lines and the edge shapes at the 4 different locations. So the network model with normal prior and hypo-prior were very good at reproducing the desired patterns. Only the network with hyper-prior could not achieve the desired goal, because this network with hyper-prior did not utilize its own sensory signal, incoming signal. This model just utilized its own internal model, making predictions, and then even if we provide sensory signal, the network just ignores the sensory signal. That's why they could not achieve the desired patterns at all. Like a selfish network. Even if you give the training signal to the network, the selfish network did not take such a training signal into account. That's why they are failing in achieving the desired patterns. The interesting finding is coming from this analysis of the internal representation of the network. We had one hidden layer which contains 70 neurons, and we applied PCA to visualize the activities of 70 neurons. Now you can see that first, please look at this one with the normal prior. You can see kind of like 4 clusters. We trained in total 8 trajectories, 4 circle lines, 4 H-shaped lines at 4 different locations. So then this network could acquire the 4 clusters. Each of the clusters represent the circle and H-shape at the same locations. So it depends on the positions of the trajectory. This network created the 4 clusters so that it can better structure their desired task. This is some kind of like an optimal network training. If you are the designers of the network model, you try to find the best parameter which can create the better internal representation as well as the better output performances. And then the interesting findings is from the network from the hypo-prior. So now you can see that the hypo-prior network has unstructured internal representation. Although the behavioral output was very good, their trajectories were very, very accurate, but the internal representation were not well structured. You can imagine that, for example, the generalizing the acquired behavior is not possible with this rightmost type network model. The reason
you are projecting the trajectory into the two-dimensional space, so you cannot say that this is not the other part is not clustered.
Yeah, we also did a quantitative analysis, how well the network acquired the clusters. And the quantitative analysis also showed that this network was not good at showing the clusters. So that we compared their ratios of their inner cluster distances and the outer, intercluster distance and the intra-cluster distances in the quantitative manner.
Distance is just one thing, you see.
Yeah.
In the higher dimensional space,
yes,
there must be some manifold, kind of manifold. Perhaps you cannot see it by measuring the distances.
The distance was measured in the higher dimensional, the original
Yes,
70 dimensional.
Yeah, still. there might be possible that there is a
Mhm.
different manifold.
Okay, yeah. Yes, you're right. The measurement there, even in the 70-dimensional space,
Yeah.
our measurement might be just one aspect.
Right.
But at least in that aspect, in the 70-dimensional spaces, we found that this network was not well structured in their internal representations, not only in this 2D space, but also in the original, the 70-dimensional space, how they clusters their 8 types or trajectories are not well, not well structured in that network.
Okay.
That's one measurement from the analysis. Yes.
I think one way to test it is just to create some generalization test.
Mhm.
And do you have like some similar generalization test to
Mhm.
test this performance?
Yeah, actually at this experiment, we trained the 8 all trajectories first, but then afterwards we also trained only with the 7 trajectories out of 8, and then tested whether the left trajectories can be created after the 7 training. And then we found that the generalization capability was highest with this normal prior network, and then it gets lower on that side and this side as well. Thank you for the question. Okay, so from this analysis, we found that only the normal prior could achieve their desired trajectories as well as acquiring the better structures. And we found that the hypo-prior network, although they were very successful in achieving the desired pattern, but as the hypo-prior network did not utilize its own internal dynamics while training. So that's why they were not successful in getting the structure in the network model. They just tried to replicate what they have to achieve, but then they did not utilize their already acquired internal dynamics of the network because they didn't utilize all its own predictions in their training, during the training. That's why their structured patterns were not well designed like this. And then by doing this analysis and the comparison with their autism behaviors, we thought that these diversities in their network patterns can be nicely correspond to the individual diversity between the typical developments and the ASDs. Our first conclusion is that the normal prior, their network, with the parameter chi for 0.5, nicely showing their result, which is analogous to the typical developmental behaviors, whereas the hypo-priors showing the different types of autism-like behaviors. One showing their failures or difficulties in achieving the desired task, that is one type of their autism, and another type, some persons with ASD sometimes are very good at achieving the desired task, but then they fail in generalizing their acquired knowledge. So that kind of behaviors or the cognitive processes can be explained by the hypo-prior network. This is additional discussions, so I just summarized what we found from the network study. So with the hyper-prior network, we basically made the influence of their internal model stronger on the network, the training. In that case, the network strongly relied on its own predictions. So that's why they could not achieve the desired behavioral trajectories in the prediction. It nicely also showing the poor adaptation abilities to the new environment. And on the other side, you can see there are different variants of their ASD-like behaviors. So this network utilized their sensory signal more strongly than its own predictions. So in that case, they can achieve the certain task, but then they fail in generalizing their acquired knowledges that might explain another type of difficulties in autism spectrum disorders. So this is the first study, and yes?
I note that you put the ADHD on the hyper-prior side, and
Yeah.
this surprises me a bit because usually what's notable in ADHD is that they are more easily distracted by the environment.
Yeah.
So you would say that being more The attention being more volatile and
Right.
distracted by the external cues would
Mm.
be that they have lower internal prior. So what is why did you put them on this side?
This is actually the suggestion. So this is actually the suggestion from their psychiatry, their medical doctors. They say that their unstable attentions might be caused by their often switching the internal intentions rather than the external sensory signal. We know that the ADHD, their typical the behavior pattern is that they cannot focus on one task. They are often distracted by many other things. And from the behavior, the studies, yes, I know that, as you said, there several researchers say that they are just distracted by their sensory signals. So the sensory signal, reliance on the sensory signals might be the one cause on the ADHD. But medical doctors who are working on the ADHD suggesting that there are unstable or unfocused attention might be more caused by their internal, their intentional changes.
Mind
Yes.
wandering and things like that.
Yep. That's why I put ADHD on this side. It's still the hypothetical, their ideas. We don't know yet whether this ADHD can be well also very explained by this. But then I think that can be the one potential, the interpretation of the difference between ASD and ADHD. Yes.
From some the Bayesian inference perspective, the parameter control the prior over the sensory is also we can build another hyperparameter to control it. So in some other study or in your previous study, did you examine this kind of meta parameter that control?
Yeah.
Because most of people they are normal, so which means they can control this parameter within a very reasonable range.
You mean the persons,
I
the
mean,
people can control the parameters,
Yeah,
or
most of people
Mm.
we say it's normal people.
Mhm.
They are normal people, so which means they can control this parameter within a very reasonable range.
Yep.
And only the ASD people they cannot. And so, do we really have this ability to maintain this hyperparameter within a reasonable range?
Yes, I think the first, though, as I have the wider range here, so the typical developed person should be able to control how strongly they rely on the sensory signal or how strongly they rely on its own predictions. Depends on the environment and also, of course, depending on how precise their prediction is. So their the control abilities of such a reliance or the hypo-prior is one of the important capabilities of typical developed person. And another point is that we don't say that the one persons of ASD it stick to one side of this spectrum. The people with ASD can also changes between or on this spectrum, but it seems that they goes to the extreme side of in this spectrum. That's what we found from the ASD, the behavioral studies. Actually, for example, if you're familiar with the autism, the behavior studies, you often see there are very big variances in the ASD's result. So the researchers often compare the TD group and ASD groups, and TD groups has lower variances between the individual, but the ASD always have the very big variances. So that's actually why it's so difficult to see the significant difference between TD and ASD. So this big variance is indicating that the persons with ASD also should be somewhere here in between their normal priors. But then some people often tend to go to the very extreme side of this spectrum. That's why they often have the difficulties in the cognitive processes and also the social communications. Yes, that's still our hypothesis. We, in collaboration with the Tojisha Kenki researchers, we try to really verify this computational hypothesis. But from our kind of observation, we think that this diversities is important, and also the traditional study often say that TD is on one side and ASD is on the other side. That's a very traditional view. But what we can suggest from this computational study is that TD is a kind of middle, and the ASDs are two extremes on the spectrum. that's a new perspectives or new ideas of this.
Thank you. It's very interesting.
Thank you. Okay, then I want to go to the second studies of the neural network model, which basically follows the same ideas from the previous studies, but we implemented the ideas into more, can I say, the easily understandable way. So the first studies, we used a very simple, like 2D trajectories in the space, but then we could not directly compare our result with their autism or TD behaviors. So now we started with their drawing abilities in the children's with and without ASDs. For example, this is the one that study showing that how the 10 years or 11 years old ASD children draw their house. Experiment that gave their example of house, and then the children were asked to replicate their existing house. One typical example you can see is here. So this boy or girl started drawing with if you are asked to draw a house, you will probably start with the contours of the house, and then you go into the smaller parts. But this boy, as you can see, they started with window, door, and then finally the contour of the house. This also showing that how their focus is located or focused on the local the informations in the processing. And this is another example. He or she failed in making the configurations, the structural, the figures of the house. Maybe one corresponds to a door, window, and the contour of the house. But he couldn't replicate the configural relationship between the windows and the door. But then another study showing that some children with autism, specifically their Savant syndrome, often show the very superior abilities in drawing. It looked like a very professional drawing, but it was drawn by a 5 years old child. This is a drawing by 5 years old, the 6 years old, the typical developed child. This is very simple but very typical drawing. So at years, at least 5 years, it's very superior to have this kind of drawing abilities. So the question is whether we can replicate this drawing behaviors using the neural network model. We basically utilize the same network model with the previous experiment, but we introduced just one module which can better replicate the ideas of Bayesian inference. And we trained this network with these simple patterns: drawing face, drawing house, and drawing flower. So we provided these 3 patterns to one single network, and then after the training, we gave only the first part of these drawing trajectories and let the network to make predictions about the rest of the drawing. So this is the result, and from there you can see the behavioral output of the hyper, normal, and hypo-prior networks. The first, this black line showing the replications of the existing provided the trajectories, and the green line showing the parts, predicted parts by the network model. And now you can see that hyper-prior and the normal prior networks are somehow very successful in achieving the desired patterns. Only some networks failed or misinterpreted the intended pattern. We provided the house-like contours, but it finally produced the face-like patterns inside because the contours of the face and contours of the house were close to each other. So this kind of interpretation were often observed, more often observed in the hypo-prior network, because the hyper-prior network produced very strong attractor in the network. So that's why they also often cause the misinterpretation between the similar trajectories. And another interesting finding is here, the hypo-prior. So you can see that the hypo-prior networks often fail in completing the missing parts. They could draw only the existing parts which were given to the network as an input, but then once the input is lost, the network could not make predictions because this hypo-prior network strongly relies on the incoming sensory signal. If there is no incoming sensory signal, it cannot make predictions. That's why they often failed in achieving the desired pattern. And especially I want to focus on this specific network, which somehow following the existing line. It never goes to the lower parts. And we found that, interestingly, the chimpanzees show the similar patterns with the hypo-prior networks. So the researchers in Kyoto University, the Primate Research Center, let their chimpanzees train first the drawing, especially using these chimpanzees' face patterns, and then asked whether the chimpanzees can also make a predictions about in the drawing. Experimenters gave a paper on which only the contours and only some of the facial features are already drawn. For example, this picture missing 2 eyes, or this picture missing 2 eyes and also nose. So some facial features are missing in the original paper. And the question is whether the chimpanzees can fulfill the missing parts or not, and then how their behaviors are similar or different from their human child abilities. So these are some examples. And the left side, you can see the result of the human girls. Again, 2.2 years old, 2.5 years old, and so on. And right side, you can see the result from chimpanzees. And they classified their behavioral patterns into several categories. And one of the most impressive, the result is here. So you can see that a human girl, 2.5 years old, could successfully complete the missing left eyes. But you cannot see anything here, which means that chimpanzees never tried to complete the missing parts. They often just follow the existing line like this, or they just swipe like this. But experimenters could never find the chimpanzee's behavior which tries to complete the missing parts. So from this experience, or the experiments, we see that our network model with this hypo-prior must be very similar to the chimpanzee's behaviors. And actually, I know that Professor Tetsuro Matsuzawa, who is the head of the Primate Research Center at Kyoto University, he often mentioned that chimpanzees live here and now, which indicating that chimpanzees missing the abilities to make predictions. It's a kind of behind theory I interpret from his word. So chimpanzees lives here and now. Humans, in contrast, lives about future. So we make predictions. That's why we also sometimes worried about our future life and so on. That's the biggest difference between human and chimpanzees. And we think that this hypo-prior may explain the difference not only between the typical developed persons with ASD, but also the differences between the species. I have 2 slides to better explain or more clearly explain what we found from that experiment. The one finding showing that the persons with their ASD often see the visual world like this. So this is a typical patterns, and this is the ASD's view. You can see that with this bright environment, that person with ASD often see this like white-out images. And we also actually know from their behavioral study that the persons with ASD have difficulties in controlling the pupil size. As you know, that pupil size are automatically adjusted depending on the environmental, the brightness. If you go to the very bright space, your pupil size gets smaller automatically. But persons with ASD seems to have, in average, the larger pupil size, one side. And on the other side, they have also the difficulties in controlling or adjusting their pupil size depending on the environmental brightness changes. So that might be the one reason why they see the white-out images like this. And another finding is that there are dotted noises on the visual scene. So here you can see the snow, but also there are like an artificial dots in the space, so like this. And currently we don't know yet what is the neural or the physiological causes of these dotted noises, but we know that the persons with the migraine patients also see the dotted noises like that. And the researchers in neuroscience already found that the very specific neural mechanism called cortical spreading regulations seems to be the cause of potential causes of the dotted noises. So now, in collaboration with the medical doctor in Osaka University, we try to find out whether the person with ASD might also have this kind of the specific neural mechanism or not. And very recently, I also found that there is one very similar and very, very exciting studies conducted at Sussex University in their Anusest group. You know that Anusest is very famous researchers in consciousness study. And Dr. Suzuki, who is a postdoc researcher in the Anusest group, created the hallucination machine. I found that he also gave a talk in this consciousness club in 2017 in the list of the speaker. I found that seems that he already talked about this story in that talk. So the basic ideas, or what is so exciting in his research, is that he utilized a deep dream. This is a neural network model created by Google. And with this deep dream, he created the hallucinations in their patients, in their psychiatric patients. For those who are not familiar with the deep dream, the very simple key idea is that the neural network model, deep convolutional neural network model, are first trained to recognize many different images. And then after training the network, the researchers or designers can clump certain level or certain layers of the neural activities. And usually, if you provide the input images to the network, and then if the network detect the prediction errors between their top-down prediction and the bottom-up sensory signal, the network usually tries to minimize the prediction error by updating the network connecting weights. But in this deep dream, instead of updating the connecting weights, they clump their neural activities here, and they also don't change the connections. Instead, they try to change their input signal in order to minimize the prediction error. So the outcomes of the images showing what the network predicts to see as an input signal. That's the key ideas of deep dream. And Dr. Suzuki utilizes deep dream in order to generate many different types of hallucinations by taking these technologies and observe and also examine how well it can replicate the qualitatively similar psychedelic in their studies. Let me give you 2 video clips from his paper. So now you can see some animals' face, like dogs, bears. They are created by the deep dream because deep dream were trained a lot with their animal pictures, like dogs, cat, bears, and so on. That's why the network always tried to predict to see dogs or animals' face. That's why the images were infected by these predictions. This is the outcome, one outcome of their psychiatry. And then also Dr. Suzuki said that this visual world seems to be very similar to the psychedelic experiences. And if you clump not the higher level of the network, but the lower level network, you can create different type of hallucinations. Here, the edge features are very much enhanced because their deep convolutional network, usually they imitate our brain visual cortex. So the lower layer, like the first visual cortex, represent only the edge features, not the shape of someone's face. So once you clump the different layer, you can show the different hallucinations. And by inspired by his study, we thought that maybe the atypical perceptual experiences in ASD can be well explained by this low level. There are some atypicalities in the predictions. The imbalance between the incoming sensory signals and the top-down predictions produces like an autism, like the hypersensitivity. So we just started discussing with Dr. Suzuki to explain better our findings in the ASD and then try to replicate using the deep dream techniques for better understanding the underlying mechanism. So here is the conclusions. And So I introduced the idea of predictive coding to explain the diversity between the typical development and the autism spectrum disorders. And key idea is that the hypo-priors can be the potential cause of ASD. This is already proposed in the original, the theories of ASD. But then by taking the computational approach, we found that we could extend this hypothesis, for example, integrating the hypo-prior as another potential cause for the autism. Or we also know from the Tojisha Kenkyu, first person study, that one person can show the different reliance on their predictions. Sometimes they show the very strong reliance on the prediction, or sometimes very weak reliance on prediction. Such an individual diversity, even in the one person, can be explained by the deviations between these hyper and normal priors and so on. So this is still the hypothetical work, and we hope that at the end of our CREST project in 2 years, we want to better show this theories and propose a new extended theory about the ASD based on the predictive coding. So yes, I want to conclude with the very, very last slide. This is my recent theoretical paper explaining how predictive learning can give the principle of their cognitive development and also the developmental disorders. So if you are interested in our work, I'm happy that if you look at our paper. Thank you so much for your kind attention.
Thank you very much, Doc. And we have our 20 minutes full of discussions. Like, if you have questions, please raise your hand and ask questions.
So going back to when you were talking about hypo-priors and hyper-priors, that like when you first, that is perfect. So I was remembering when you were introducing the first person studies, and how when you were comparing like the sensation of hunger with this multi-array of sensations that the atypical, the ASD people have. So when you talk about that, heavily relying in sensory information, do you just mean, so the first part of the question would be, do you just mean external sensory information, or you mean both external and internal sensory information? Because from the testimonies of the ASD people that you collected during the research, they seem to be exceptional at interoceptive judgments of what's going on with their inner sensory information. So when you say that hypo-priors mean an extreme reliance on perceptual information, on sensory information, do you just mean external or both external and internal?
Actually, both. I did not explain clearly, but then here we want to integrate the ideas of interoception as well. Basically, most of the studies are focusing on the exteroceptive sensations and how people are sensitive to the exteroceptive visual audio signals. But we know from the first person study is that their integrations of their interoceptive sensation and the exteroceptive sensation seems to be another core problem in ASDs. Some research showing that, for example, the persons with ASD are very sensitive to their heartbeat, but then they are not good at making their or interpreting their emotional state. So it seems that they are very sensitive to the lower level interoceptive sensation, but then by integrating such an interoceptive sensation, they are not good at making their higher level, their cognitive processes.
This brings me to the second part of the question, that would be, do you think like the same way when we were comparing ASD versus non-ASD, like the non-ASD person is very good at saying I'm hungry, the ASD person is very bad at saying I'm hungry, but can probably describe all these feelings that build up to being hungry much better than the no ASD. So this is a speculation, like I would like you to know your opinion. Since priors are in principle unconscious, right? You don't decide what kind of prior you want to have given a certain situation. Would you venture to say that there is something like basic sensory interoceptive level and like a conceptual prior level and some sort of high order representation, but of an unconscious order and in terms of interoception prior? Would you venture to say that the problem is at that high level, that they are good with like sensory interoceptive information, but like there is some sort of more high order network actually giving a meaning to this sensation,
Mm.
like as hunger or anything.
Yeah. Yes, I agree with you that I think the most of the ASD research showing that the person with ASD are very good at recognizing the lower level perceptions, but have difficulties in the higher level cognitions. I don't know that the opposite, there are evidences from the ASD studies. But still their open question is that at which level they got these difficulties, whether this their top-down or how they minimize, or where they try to minimize the prediction error, at the lower level or higher levels or somewhere else. So still it's an open questions. But it seems that there are many of the behavioral studies and also first-person studies showing that the lower levels are more sensitive side on the ASD, whereas the higher level cognitions is more difficult in ASD. That's a kind of consensus, the findings from the ASD study.
So is the tendency consistent among other sensory modalities?
Yes, I think so. We now studying the audio hypersensitivity as well, and the audio hypersensitivity also show the very similar phenomena with the visual hypersensitivities. So we can apply the same ideas or hypotheses to the audio hypersensitivity as well. And we are not so familiar with the other, like a tactile or smell sensation. But as we know that our human brains are kind of, how can I say, have the kind of unified their mechanism for their, regardless of their perceptual, their modalities. So we think that their underlying neural mechanism for the different modalities could be shared with the different.
Subjects has has same tendency for other modalities, and hyper has same for other
I think that
modalities.
can be switched. So
Okay,
even
yes,
even there one persons can have their sometimes very hyper visual sensitivity, but also the very hypo visual sensitivity. Even in one modality, they can be both. They can have both hyper and hypo.
You
So-
can check the tendency.
Sorry?
Or you can check the tendency for same subject.
Yes, from
Or
the
it
question.
fluctuates accordingly. I mean,
Within this one subject, they show the two types of the extremes, hyper
Okay,
and
yeah.
hypo. From the questioning, also there are some cognitive experiments, how they are sensitive to their sensory input or priors. And such an experiment have been conducted in the cognitive science, and they show that just one person can be both. Sometimes very strong reliance on the priors, sometimes very weak reliance on the priors, even in one cognitive experiment.
okay. Another question is, can you put the age on that? How as children grow, how do they move? Or
Within
is it
system.
hard to define? How the development
Yes,
affects?
that's an interesting question. Actually, we actually show that of course, because children have less knowledges, less experiences, their prior must be very weak. They cannot utilize their own knowledges before because they don't have so much knowledge yet. So they have to rely more on the sensory incoming signal. Actually, we know that the visual illusions or auditory illusion do not observed in small children regardless of the ASD or typical persons. Small children do not have illusions because they don't utilize its own predictions. That's the one evidence is showing that they have the very weak priors. They relies more on the incoming sensory signal.
Okay, maybe the lower part. Maybe
Yes.
the hyper grown up.
Yes,
I mean,
yes.
they
Once
tune
they
too much.
acquire,
Yeah.
gradually move to the stronger pliers. I'm not sure whether it depends on
Yeah, we
what
should stop.
experiences they have. Yes.
I have a general question. To get the posterior, of course, you need the prior, and also you need the likelihood. So, in your talk, you very focus on the prior for the ASD patients, but the likelihood is also very important. So, I just curious about why you so focus on this
course, the likelihood or sensory signals is also can be different between TD and ASD. In our current study, we have not done any experiment yet, but we don't ignore that hypothesis as well. So maybe in the future, we want to test what happens if we modify their sensory incoming signals in our predictive model. So we just started with the hypo-prior hypothesis to test the extended service, but we don't deny there are another possibilities of the autism. And we also know that at the sensory level, the persons with ASD often have the different reactions to the visual signals, like pupil size control, and also I forgot the English term, but there is a specific sensation in our ear, which reacts to the sound amplitude. And then the researchers already found that how their certain sensors in the ear would respond to the sound. It can be different between typical different persons and autism. So there must be already the differences in the sensory level, not only our predictive brain.
The reason I ask is because usually even the likelihood is conditional on your model. So it's like if you have different model, you will have a different likelihood estimation. So it's also kind of prior. And so it's like so one part is there is a prior to compute Bayesian posterior, but actually probably the model part is also very important. Yes, and then things like it's kind of missing part in this study.
Yeah, I completely agree with you. Yes, yeah, we should definitely address that issue as well in the future. Thank you for your comments. Yes.
So the very interesting part where you have the patient, the people with ASD, matching a visual filter to reproduce the experience.
Yeah.
If you ask me to match a visual filter to reproduce my experience, I would not be able to do that because I always experience so it's a kind of El Greco problem where if I have my migraines, so I could describe my migraine because I don't have them everywhere in my visual field and not always. So it seems to indicate that people with ASD must have some kind of fluctuating experience because otherwise they might not be able to match this kind of filter. So they know that sometimes they experience things that way and sometimes they don't. It's not something that is stable.
Yeah.
So is that integrated in your perspective? Because it's not exactly a question of having a hypo or hyper-prior. It's having fluctuating priors or something like that.
Yes, it's a very important point. Actually, the persons with ASD also do not always have hypersensory sensitivity. That's why they can reproduce their experiences. Only when they go to the very noisy place or very cloudy places, they have that strong hypersensitivity. That's why in the experiment room, in a quiet room, they can also have a very quiet visual world, like a typical liberal persons. That's why they can reproduce their like a dotted noises, high contrast image on the computers. That's a very important point. And such fluctuations happens. One reason there is that their environmental, the conditions changes. So as I said, the cloudy places, noisy places often produces the hypersensitivity. So environmental changes is the one reason for the fluctuation. Another reason for the fluctuation is their mental or their physiological state. Many persons with ASD say that when they get tired or when they have cold, they have hypersensitivities. So depending on their health conditions, their hypersensitivity also drastically changes. That's another important point, which has not been integrated in our model yet. Our model just utilizes their exteroceptive sensation and no interoceptive sensation yet. That's not very important issues for the future. Yes.
Yeah, can I ask again about the neural network model? So I point. So, as I understand correctly, so the how do you formulate this hyper-prior in terms of neural network parameters? Like, is it included in the function of error, of predicting error?
So when we utilize this is the updated version of the
Yeah.
network. So the network predict the next time step signal.
Yeah.
And we always train the kind of temporal trajectories. So in this case, we provide the XY position at the time t, and then the next time step, it has to move to some directions in order to draw the circle or shape of the house and so on. So it's a temporal trajectory, temporal signal.
Okay.
So the network predicts the next time step, the XY positions.
Mm-hmm.
And then by continuing this process, the network tries to reproduce the face-like patterns or house-like patterns just by continuing predicting the XY positions. And then we utilize these predicted XY positions as an additional input to the network. When we train the network, we provide the training, the desired patterns, desired trajectories. And then the network also make predictions about their next time step. So when we provide the input signal to the next time step, we combine this incoming, the training signal, with the predicted signal based on this Bayesian inference ideas. So depends on how sure the network is about the sensing signal or about the predictions. The network changes how they integrate these input signals.
Yeah, so am I understanding correctly that you measure actually like scale divergence between two probability distribution, or you just as a error you just measure the difference between XY position, like you measure the I don't know the Euclidean distance, and then you propagate it back to.
For the trainings.
Yeah, for
the trainings,
yeah.
there are so
Which
that
kind of objective function do you use?
for training we utilize the back propagation through time for the recurrent neural network model, and then we compare if I remember correctly, we compare the training patterns with the integrated patterns of the predicted signals of the network. And then we updated the connecting ways of the network.
What is the loss function to be minimized or maximized?
The loss function is the same with the normal, the recurrent network trainings. So there are differences between the trained patterns with the predicted patterns from the network.
Do you do some early stopping of the, you see in the neural network, you need to stop somewhere
Yeah.
a priori.
Yeah.
I mean, artificially. So that is the problem, you see.
Yeah, we measured their convergence of the network. So we compared every time step their error values, and then if their error value does not decrease anymore for the certain period, we stopped the training. So the different conditions have different lengths for the training. Depends on their convergence of the network. Yes.
In all of your examples, you were using Gaussian or normal distributions. But and I don't know whether that was just for simplicity of presentation or to assume those in the actual computations, but there's certainly, for hierarchical Bayesian modeling or learning, if they're asymmetric or non-Gaussian priors or distributions, it can lead to instabilities where the prior gets more and more biased because it keeps pulling the data, the input in the same direction, and then it reinforces the model, and it gets more and more extreme. I wonder if some issue like that could lead to either the hyper or hypo strength of the priors, because you can almost completely eliminate the prior in some range of inputs. I don't think, I'm not sure the model needs more free parameters, but I just wondered if you thought of that.
So you mean even if we set the parameters from the designer point of view, the network itself changes.
But it assumes, if I understood correctly, maybe I didn't, it's assuming that the prior is some Gaussian distribution, not, for example, some power law or some other
Yeah.
box function or something, or particularly something asymmetric, a triangle or something.
Yes, because this network predicts the variance as well. So the variance was used as a really the variance for the Gaussian distributions. So we assume that it has these Gaussian distributions like this.
Anyway, it was just a speculation that if some class of people use Gaussians only come out of the central limit theorem, which isn't really applicable here, but so if it might be a deeper explanation for why some people have these unstable hyper or hypo if they're somehow their innate prior is not a symmetric function.
I think the terminology proves you right. If your prior is not normal, then you're not normal.
Yeah, I have never thought about such an asymmetric priors patterns, but that's very interesting.
Or maybe we can measure it by experiment.
Yeah, I think that might be possible.
Yeah, we may be able to measure the shape of the prior with some assumption. Right? Maybe we cite some
But in most of the case, the normal assumption is a fake assumption.
Yeah.
You know, the
But you could do an experiment like that, putting in something other than a Gaussian function.
But